Okay, so let me just talk about them first. Yes. Okay. So one of the questions that I talked about, one of the examples that I did was using matrices to solve these systems of differential equations. Okay? Right, so you've got a system of differential equations. The matrix in it has got constant values. The easiest case is the top line where you've got a diagonal matrix. So people were asking me yesterday, and it's a good question, how do you solve a problem like this? I've forgotten how to solve it, right? Which is a fair enough question. Well, if you're ever worried about these sorts of things, you can write it like this. And it's a separable differential equation, right? It's separable. So, you know, what do you do with the variables here? You separate the variables and you integrate. Okay? So if you're ever worried about solving these kind of problems, you can most of the time break it down to something that you've seen before. Okay? Like I just think, well, you know, you want something that when you differentiate it is the negative of the thing. Well, it's got to be an exponential. Okay? Oh, hang on. I've missed out the y1 there. How you bring the y1 down there? There, that's better. Whew. Okay? So when you're solving these problems, we sort of assume that you're okay with separable differential equations, you're okay with linear differential equations. These type of questions will be in lab test 2. Okay? They will be in lab test 2. But not, yeah, and including matrices, right? Including matrices. All right, so we are into the final part of this course now, right? It's sort of chunks of 3 chapters or 3 sections, right? We've done 1 to 3 and we had a lab test on it. 4 to 6, lab test 2. 7 to 9 will be the remainder, okay? So that'll be sort of heavily weighted to the final exam. But you won't see any of this in lab test 2, okay? We started this yesterday, and the idea, let me just make a few more notes. I showed you how to compute a few transforms, great, but let me show you sort of the slightly bigger picture here. All right, so the motivation one of the reasons that we're learning about these transform methods is because historically they've been used to solve problems involving differential equations, okay? And that's really our aim. So let me give you an example. Initial value problem. Let's say you have something like this. Y double dash plus y equals this, okay? So the first question is, what is the right-hand side, the u of t minus 1? We talked about this at the end yesterday, okay? So here's a picture at the bottom of the table that I showed you yesterday involving this, I guess you can call it a jump function, or you can call it a Heaviside function. Somebody talked about the Heaviside function yesterday, right? So basically, this function, it's 0 for t less than 0. It's 1 for t greater than 0. And at 0, it's kind of the average value of the two limits. Okay? Now, I did say that the actual value, the in-between value doesn't matter. It could be 1,000,000 or negative 1,000,000,000, right? It doesn't actually matter. It's just nice that we've got a little bit of symmetry and averaging there. Okay? So, all right. let's go back to this kind of problem within this context. Okay, what is u of t minus 1 going to look like? So if that's u of t, right, that's how we define it. Who can tell me on this early Wednesday morning, week 7, what do you think the graph of u of t minus 1 is going to look like?
Would it be just the same but shifted to the right by a unit?
Perfecto. That's exactly how I would think about it too. It's the same graph as you see already drawn, but it's just moved 1 unit to the right. Okay? The biggest mistake that I see students making is they go, oh, I can shift things left and right. Because it's a negative sign, it must somehow go to the left. Not true. It's the opposite. Right? You shift it to the right. If you see a plus sign, you shift it to the left. Okay? So in this case, let me put an extra initial condition in there. Okay? All right. So in this case, this form over here, the jump would occur at 1. Okay? So if I was, drawing a little model here for this right-hand side, it would look something like this. Okay? So you've kind of got 2 problems here. You've got 2 sort of differential equations, or at least 2 right-hand sides. So if I wanted to write this out in full, I could change this like this. Okay, it's 0 when t is less than 1. It's a half when t equals 1, and it's 1 when t is greater than 1. Okay? So let's say this is a vibrating system, something like that, and the external force is the right-hand side, the u of t minus 1. You can kind of think as a switching kind of phenomenon going on here. Yeah? So for t negative, for t less than 1, nothing's happening with the right-hand side, it's just 0. Right? And then at t equals 1, it sort of magically gets pushed and switched on, and then it's a constant input. Okay? Now, if you were solving this using first-year techniques, can anyone suggest what you might try? You can do it using first-year techniques. It's not very pretty though, but what do you think we might try from first year if you were given this problem? I know it's early. It's not a trick question. April Fool's was yesterday. I hope you had a good day, by the way.
You could try limits.
Oh, yeah? Yeah? So what's the important point here? Talking about limits, what's the important t point in the picture? 1, right? So you want to know what happens sort of at or near 1, t equals 1. Okay, so that's good. So let me write this out a bit more. So if I'm going old school style, first year maths, it would be this. Yep. Okay, so if I write it out like that, does that make it easier to solve? How might we tackle it? We know something changes at t equals 1, right? And as we approach 1, we've got sort of different limits, as you were sort of implying before, right? How might we do it? It sounds like a pretty easy problem because, the right-hand side is either 0, a half, or 1. Any ideas? Well, let's make it a little bit easier. What happens, oh, sorry, less than -1 down the bottom, not equals to 1. Listen. So what happens if I do this? I'm just going to cover up. Bloop. Okay, y double prime plus y equals 0. Can we solve that? Y double prime plus 1, y equals 1. Can we solve that? Yeah? Y double prime plus y equals 1/2. Can we solve that? Yeah. So you've kind of got 3 different problems here rolled into one. So the way I would do it, if I was using first year techniques, I would just say, okay, I'm going to solve the case when t is less than -1 and get a function, right? I'm going to solve the case when t is greater than 1 and get a function, right? The middle case isn't so easy because we're just at one point, but we want to have some sort of jump or connection, okay? All right, so these are the kinds of problems that we're going to look at using Laplace transforms. Okay, that's basically it. Linear problems, linear differential equations that have constant coefficients, so there's no like t's or whatever in the coefficients, and the right-hand sides might have jumps in them. Okay, there might be like heaviside functions or switching functions, things that you can turn on and off. All right, that's where we're going. Okay, but to work this out, we need some sort of machinery, and we need some sort of transform to sort of get us there. Oh, positive one, sorry. Yeah. Sorry. My symbols are not working for me. There, that's better, because the change happens here. Okay, sorry about that. Thank you for pointing that out. Okay, so 3 bits. T less than +1, t equals 1, t greater than 1. Okay, I don't know what I was saying, -4. Okay. All right, now, yesterday I did show you some basic transforms. Okay, we sort of worked through these together, and the idea is to define this Laplace transform in terms of an integral. Okay, so you've got a function of t, you plug it in there, you multiply by exponential, and you integrate over the half line. Okay, and so there was a really good question saying, well, what are we doing when this kind of, when we make this thing happen? Okay, the best I can come up with there is that you're transforming a problem right? And you're solving the transform problem. And then what we're going to do later is transform back. Okay, so think of the differential equation I showed you before, right, with the jumping function. We're going to take that, we're going to transform it to a simpler case that we can solve. We're going to solve that simple case, and then we're going to untransform everything back to the original sort of setting. Okay, so why does this involve an integral? Well, you can kind of think about differential equations involving derivatives, and integrals undo derivatives, right? And also for these kind of problems, where is it? For these kind of problems, you can relate solutions to the exponential function. So maybe that's one reason why they've got this exponential in here. Okay, but at the moment we're just going to do some transforms, calculate them, and then see what they are. All right? So the first thing we did was this exponential e to the negative 2. So what's the transform of that? So put that in there, multiply and integrate. Okay? The only thing we really had to remember was our Math 1131 improper integrals. Okay? Improper integrals. So they're not integrals behaving badly, or sometimes they do, but we interpret that infinity sign as something like the following. You integrate over a finite interval and then you take the limit. Okay? So as long as you can manage that, no worries. And your answer should be a function of s, because we're integrating with respect to t in the original transform, but there's an s in there too. Okay? All right. So we came up to the end of this problem. And then I said to you, don't worry. We're not going to do endless improper integrals. Yeah? So what do we use? We use, in many cases, we use a table. Okay? So the table that I showed you was this one. Okay? So another good question at the end of yesterday's lecture was, I showed the one that you get in your exam, and it's not exactly the same as this one. But it's probably enough. This is probably too much, but the one that you get in your exam is the important one. Okay, but I would say that, you know, whatever's here you can always get from the one that you get in the exam. So let me show you the exam one. Okay, so allowable materials. Okay, so same sort of basic things. There's no gamma function, you don't need it. And then there's Laplace transform of derivatives. And so you can see in my one, if you just look at it side by side, there's a few things here, but you can get these things from the basic table. Okay? So I think that's important to know which ones are you going to get, which ones do you need to know. Okay, actually you don't need to know anything. You can, you know, as long as you have a basic table, you can use that to get all the other transforms. So I wouldn't stress about it too much. Okay? Now I also said that when we get down here, this is where we're going to start using transforms to solve differential equations. Okay? And that's the key thing. If you can understand one thing about Laplace transforms and their relation to differential equations, it's this. If you transform a derivative of something, then the transform undoes the derivative. See how there's a derivative there and no derivatives there? Derivatives there, no derivatives there. I mean, these ones are okay, but they're just initial conditions, so that's fine. Derivatives there, no derivative there. So this goes back to my earlier sort of, I don't know, position that these things work, and they will work, because they undo derivatives in a nice way. Okay? They undo derivatives in a nice way. Okay? All right, questions so far? Comments? Observations? Criticisms? What's happening at home, everyone? I'm out of sync. Get back into sync. If only life was that easy, right? Get back into sync. Oh, I can't get back into sync. What does that mean? Get me out of here. Okay, that's good. Okay, questions? So let's do a couple more problems and see how we go. We had a bit of a game yesterday about using the table. So, you know, so the Laplace transform of the constant function 1 is 1 on s. The Laplace transform of the constant function 3 will be 3 on s. Okay? The constant function of, the Laplace transform of t will be 1 on s squared. And then you have a general power rule, right? So here m's an integer. Okay? So the Laplace transform of t squared would be 2 factorial over s to the power 3. So it's pretty easy to read. Sometimes you'll get questions where you can't see the function down the left-hand side, and people panic. They go, oh, I can't see it. Where is it? What do I do? Right? We need to do some work then. Okay, you need to do some work. So sine, the transform of sine of 4t, given that, would be 4 on s squared plus 4 squared. So, you just read off the table. The best prep you can do is to get to use and know how to use a table, okay? All right. Now, down here, there's a few more things, okay? So let's talk about this. Okay, so u of t minus c is this heaviside function that has a jump in it, right? So according to that table, the transform of that is this, okay? So going back to my previous problem, if I took the transform of both sides of that differential equation, so here and here and here, I'd have to know the Laplace transform of u of t minus 1, okay? This gives us a way of computing it. Now, if you're ever unsure where these things come from, you can always just use the original definition at the top of the table, right? It's an integral and you multiply and you integrate, okay? Let's have a look. So here, if I'm multiplying some function with an exponential, then I do a shift in the transform of this function only. Let me say that again, because this is a special theorem that we'll learn called the first shifting theorem, okay? The first shifting theorem. So this is like F, S, T. So if you're, let's say g of t is, I don't know, t squared or something, right? To compute the transform of that, it would be, you would compute the transform of t squared and then shift it. So the exponential doesn't really have anything to do with it apart from that value up there. Okay, but we'll look into that. We'll do some problems because it's quite an important part of the course. This thing here we've got heaviside function times g, so, and these are both shifted, c units to the right. This is SST, the so-called second shifting theorem. That's also an important thing that we'll look at. Okay? So, sorry, I've put that on the wrong line. No, I have, that's fine. Okay, there. All right? And then down here, it's transform of derivatives, and that's where we're going to use the ideas to solve differential equations. Brilliant. Okay, so the table's great. Let me just... Yep, all of those things are in the table that you get for your exam. I'm just checking that now. Okay, so let's do a couple more examples. All right, let's do a couple more. So down the bottom, I've got L of 5t plus 3. So let's have a look at this for a second. L of 5t plus 3. All right, well, the transform of this thing can be written like this. Does anybody know why? So here I've sort of broken things up using the transform. Does anyone know why I can sort of make that simplification? Anyone? Anyone? Yeah, hang on.
Because you can do that with integrals.
Yeah. It's an integral operator, and I know I can split integrals up. Why can I split integrals up like that at a higher level? Does anyone know? Yes.
Because they're linear.
Yeah. So you guys rule, okay? Yes, it's a linear operator. Okay, it's a linear operator. So with linear operators like integration, differentiation, you can break them up, right? You can break them up. And so you may as well do that. Okay, so let's say I had to get the Laplace transform of t and the Laplace transform of 1. I'm going to ignore the directive from the question. I'm not going to use the definition here. I'm just going to use the table. Okay, so let's work it out. So this is just from a table. Okay, so I'm going to go back to my table. I want the Laplace transform of t. So I look over 1 on t squared. Oh, 1 on s squared, sorry. And I want the Laplace transform of 1 on s. So I would say, okay, that's going to be 5 times 1 on s squared plus 3 times 1 on s. Okay. And the reason I'm showing you this and not the actual definition is that when you're doing problems, you hardly ever use the definition, right? You hardly ever use the definition. So, you know, that's also very good. All right, so let's make a conjecture about part B. So C and D are constants. You can see the 5 went there, the 3 went there. Well, I would say that this is going to be something like C on s squared plus D on s. Okay? So pretty straightforward, I think. Yeah? So let me radically flip the script now. What happens if you want to go the other way? Because I've got this mantra of saying, oh, you transform the problem and you solve it, and then you transform everything back, right? This is what these kind of symbols are referring to. It's called the inverse transform, the inverse Laplace transform, okay? Yep. And you may think, oh, well, it's easy to take a transform, so it should be easy to undo everything. It is, but to get really down into the definitions, you need a complex analysis, which is not in this course. Okay? So this is another reason why we use the table a bit, because if we go to our table, usually we would start over here and then move over here, right? But what happens if we started here and moved there? This is how you can compute an inverse transform. Okay? So let's think about something. Let's say we've got I don't know, we've got the inverse transform. We want this, right? We want the inverse transform of 1 on s squared. What would that be from the table? T. Right. It's not an April Fool's joke. We look down the right-hand column until we get something like that, and then you go over there and it's T. Okay? So this is how we transform back to our original kind of setting. Yeah? What about something like this? If I told you the crazy thing. Let's go to... What would the inverse transform of that be? Who can tell me? Yeah, sine 2t. Exactly. Right? So you go down here and you go, all right, I want to find something like that. going down here, oh, I sort of like that, and for b equals 2, and then you just look over. Okay, so that's how you get back. That's how you do the inverse transforms. Okay, so you can see the table is pretty important because you can go both ways. You can transform something, you can untransform or transform something back. Okay, you need to know how to go both ways with this table. Okay, so let's have a look here. The inverse transform of 1 on s plus 3. Let's have a look at that. Right? Well, go back, go down. 1 on s plus a. So if a equals positive 3, I look across and it would be e to the negative 3t. Okay? What about... Oh, we just did this one. Okay, t. Okay, what about if we had something like this? 3. Okay, 3 would be just 3t. Okay? Questions? Not super difficult, right? You just need to just get into the groove of using a table. Do people use tables in other courses? In engineering? Which courses? What kind of tables do you look at? Like these sort of transform tables or something else? Yeah.
In thermo, you use steam tables for all the values for all sorts of stuff.
Are they constants or like? Yeah. Okay. So well-known constants from the problem.
So they give you like different temperatures and then different pressures and then the well-known constants based on those temperatures and...
Got it? Cool. Yeah, no worries. I mean, when I read an engineering paper, they've oh my God. Oh my God. This is definitely going up. Okay, I'll come over to you in a second, don't worry. I was going to say that those tables probably aren't as difficult as these ones, but just for like, oh my God, it's worse than statistics and probabilities. Oh my God. So hang on, so you get this. Who are these guys? Do they work at UNSW? First published 1964. I love it. Okay. Yeah, so that's this is not as extreme as this. Did you have to buy that?
Yep.
Oh man. Maybe I should start selling Laplace transform tables. Imagine that.
I was just going to say for business studies, I use times tables.
April Fools? Oh! Times tables, yeah. Okay, so like I know we're all sort of joking at the moment, but one of the biggest problems that I see with students is they think the table looks easy, and then when they come to use it, they're like, oh, actually, it's not as easy as I thought. Okay, so just master the table. Yeah, that would be the best piece of advice that I can give. Oh no, don't worry. That'll be please don't monopolise the Laplace transforms. I won't. Don't worry. I have a strong commitment to open education. You know, don't worry about that. I won't. Please don't monopolise the Laplace transforms. Yeah. I won't. Don't worry. I have a strong commitment to open education. Muting. There. Yeah. Just shut up. All right. All right. So this next part, and I won't show this to you much today, is the first shifting theorem. Okay. So sometimes when you do problems involving differential equations, you can write the functions that you're dealing with as a product involving an exponential. Okay? So this is sort of your original form, and you want to compute okay, so an example here is something like this, where okay. So you've got a nice friendly function that's a polynomial, t cubed, and you've got a value of a. A would be -2 in this case, right? So what is the first shifting theorem? It's here. Okay, now this is in the table. It's in the tables that you get, which is nice. You don't have to remember it, but you do have to know how to apply it. Okay, but let's actually unpack it first. It says that if you take the transform of a product, then you basically forget about the exponential. Right? You compute the Fourier transform of this g function, and then you shift it a units. Okay? So there's a certain art form in this in using the tables and then doing some algebra to shift the function. Okay? So why is that true? Well, I'm glad you asked. To prove this, you would just use the definition of the transform, right? So transforms here. Right? And so you can bring those two things together. Yep. And that is this shifted. Okay? It's a cute little proof. You might be asked to replicate that maybe in the exam, but it's pretty easy, right? You just use it. Whenever you're in doubt with a problem like this, go back to the definition and look at it, okay? In this case, we didn't even have to do any integration. All right, so how would we actually do a problem using this? Now, students get stuck on two things in a problem like this. They either find the table difficult to use or they can't do the algebra. Okay, there's two things. Okay, so let's have a look here at part A and see if we can do it. All right, so here, use the FST, A equals -2, and G of t equals t cubed. All right, so the first thing we're going to do is we're going to compute the transform of little g of t, right? Once we've done that, we'll shift the transform by a units. Okay, that's the idea. So from a strategy point of view, bless you. Okay, shift our G of S a units. Okay, so let's do it. So let's go back. So the burning question is, what is the Laplace transform of t cubed? Okay, so let's go back to our table. Do I have it? Yeah. Okay. You can tell me. What is the Laplace who can tell me? What is the Laplace transform of t cubed?
6 on T4.
Yeah. Yeah, 3 factorial on s to the power 4. Yeah, which is exactly what you said. Okay? All right, so it's going to be okay, and this first shifting theorem. You've got to be careful how you say that, right? Like, remember one time I'd posted my first video on YouTube, and I had the first shitting theorem. People were pointing that out. It wasn't a highlight. Now we've got to shift it. Okay, so by the first shifting theorem, all right, it's going to be g of s minus 2. Okay, so this is our g of s here, right? So in this case, a is negative 2. All right, so what are we going to get? We just replace s with s minus 2 in brackets. Okay? So it looks easy. It is. I would say it is. It is supposed to be easy, but you've got to be able to use a table, and you've got to be able to make the final substitution. Okay. Questions? Oh, bless you. Yeah, it's all right. Got a tissue or something? Questions? Comments? Observations? Criticisms? That's the first shifting theorem. Okay? The first shifting theorem. Now, of course, you can undo things. Look at part B. So we've done part A. We're super happy. Part B, inverse transform. Okay. Who thinks they can do part B? Who thinks they can do part B? If not, just nominate someone that you think would be great. We're going the other way now, right? So, what do we need from this one? So we want to sort of start over here and go back that way, right? So what would a value of A be here? What is a value for part B, the second problem? What could a value of A be? Not quite 1. Good guess. Let me write it out a bit more. So you're on the right track. What could A be here? -1. Partial marks. Somebody emailed me a while back saying, I made a mistake in lab test 1. I left off the negative sign. Can I get partial marks? No. Okay, so in this case, A would be -1. Okay. All right. For respect, on a Wednesday morning, what would g of s be in this problem? Again, it's coming back to algebra now. Big G of s, what would it be? If big G of s plus a equals 1 on s minus 1 all cubed, what is big G of s? No, we're talking about s's. Talking about s. So we haven't got to the inverse transform yet. So this is still, we're still in this s space. So I think you've jumped a step. What about before that? Yeah, 1 on s cubed, exactly, you rule. Right? And then we're going to inverse transform that, which is, yeah. Right, so we can go up here. It's not quite what we want. It's not 2 on s cubed, it's only 1. So we have to divide by the 2, which is what you're saying. Okay? So now we can multiply this, that by that, to get our answer, right? So by the first shifting theorem, we're going to get e to the t times 1 on 2t squared. Okay? There it is. That is the inverse transform of that bad boy there. All right, I've gone over time. Let's take a 10-minute break. Come down, ask me questions if you want to, and just relax. We'll start again in 10 minutes. Hello. You disappeared yesterday. You were like,
sorry, I had a meeting.
no, it's all right. Like you're like out like a shot.
Can I just look back to that page?
Which one? Page. Is there a number? Oh yeah. Oh yeah. Is it this one?
No.
Is
There's
it?
example B from the start of the inverse of Laplace.
Okay. Is it that one? No, that's one I just did. Or is it that one?
This one.
Okay. Yep. No worries. Yes. Hey.
T squared.
Yep.
This one. Shouldn't it be on top?
Oh yeah, it should be. We're not dividing by it. Yeah, thank you. Sorry. Let me... Times. Sorry, I'm not sure why I'm dividing there. So e to the t... Hang on, let me write it out. E to the t times 2 times t squared over 2. See? Even I get messed up sometimes. There. Better? Happy? Okay. Just make that change, everyone. Sorry, e to the t times t squared all over 2. Yes. All right. So, we're a little bit ahead in the lectures. We're probably maybe 2 lectures ahead now. So I thought today, because it's still early and everyone's made the effort to come, I thought I might talk about some revision questions for lab test 2. Is that okay? Is it all right? Yeah? I think we can pause Laplace transforms until Friday. So lab test 2, same sort of environment as lab test 1. The difference is you get a how did I do button, but you can use it at most once per question. Okay, so be wise about how you use it. Yeah? And let me know how it goes, because I'm curious as well. Right? At least you get a how did I do button. In first year, you didn't get one, right? Did anyone get one in first year? First year maths? Did someone get it? No, okay, that's fine. That's fine. So there's something there. All right. So this morning, I was going through some of the questions. And there seems to be 3 chapters worth of questions. So double integrals, ordinary differential equations, and matrices. Okay? So let's have a look at some of the questions. Some questions are easier than others. Some are more difficult. You just need to choose your time and use your time appropriately. All right. So this is one of the entry-level questions for double integrals. What makes this question easy? Can anyone tell me? Like sometimes I say things are easy, sometimes I say they're not. What makes this question easy?
There's no variable in the integrals.
Yeah. So if you look at the integral signs, there's no x's or y's. Okay. So what is our region of integration for this problem? What is its shape? It's a rectangle. Exactly. Do I need to draw a picture? Not really. I can if I want to. Right? I can if I want to, but I don't have to. The other nice thing about this integral is that it's the product of one function of x with one function of y. So what does that mean? I've shown this to you once or twice. What does that allow us to do? Anyone remember? Well, it means I can write them as the product of 2 single integrals. The product of 2 single integrals. So if I was doing this problem, and here's one I created earlier. Hopefully that's coming through clear enough at home. You see how, you don't have to do this, but you see how, maybe I'll just put a bit of extra writing on there. So you see how I've turned a double integral into the product of 2 single integrals, right? I've turned a double integral into the product of 2 single integrals. Now you don't have to do that, but I like to do it. Bro, are you back with us? Hello? Hello? I'll come back to you. Bro, is everything okay?
Oh.
Are you with us today or not?
No, I just came for the next lecture. So.
Okay, you got to go. Like, it's more comfy out there, and if I look up and I see you're not paying attention, my heart sinks, man. Like, I think I failed as a teacher, right? Like, I recognize most students in this course, but I don't recognize everyone. So I'm like, oh, what am I doing wrong? I'm a disgrace to the university, right? So thank you for your understanding. All right, so there was a question.
Is it just the same as treating y, the square root of y as a constant when you do the first integral, right? Yeah.
Yep. So people's minds get blown, right? People's minds get blown. They're like, how can you do this? Well, you're kind of doing this anyway when you do the calculation, right? You're kind of doing this anyway when you do the calculation. So is it necessary? No. If you don't like it, then don't use it. Okay? But I think it's nice because it breaks it down to what you know from high school. Okay? And then you just do the bits individually and you multiply together. Multiply them, I think you get 224. Now, if you get a question like this on lab test 2, you should be pretty happy because that's 5 marks, I think. Right? It's not bad. Although I do realise there's no half mark, so it's either 5 or 0. Yeah. Okay. What do people think at home about this thing? How did we do? Shall we use our one? How did I do? Oh, thank God. Right. What do people think? At home. Oh, what did I do? There you are. Yes, I got it. Okay. What do people think? Would you use this method? Would you recommend it to your friends? Or is it too confusing? Who likes it? Show of hands. Who's not sure? It's okay. Diversity is a good thing, right? You don't have to do it. Some people, they just want one way. They're like, just tell me one way to do all the problems. That's fine. It may not be the most efficient way, but if you only can handle one method, that's fine. I've got no objections to that. You know? You know, people who do this, 16 minus 9. Oh, okay. Oh, 16 minus 9. Oh, no. Right. Anyway, you just do what suits you. Questions? Like this really is the entry-level double integral problem, right? The starter pack.
This is probably a very simple question. I just don't remember. How do we decide which interval to put for the x?
Yeah. No. This is an excellent question, right? So the way I do it, and the way they want you to do it, and the way they lay it out is, you got, so they're your x's because they're on the inside, and the outside ones, they're for your y's. Okay? So look for the inside dx or the inside dy, and it'll be the inside integral limits. And so that's how it works. Because it's easy to mix them up, right? Sometimes I just look at it and I do it, I mix them up and I get the wrong answer. So okay, I won't do that. All right. Okay, another one. Next. All right, for everyone at home. Oh, okay, I won't do that one. Same sort of problem. Now, what's even, can I split that one? I can split it up into 2 bits, right? And then the x, y I can split up. Yeah? So if I wanted to simplify this massively, I could just go, okay, well, it's the integral of 4x cubed, whatever, plus 12 times the integral of xy. I could do that if I wanted to, but you don't have to. Okay? You don't have to. So, you know, one way is to break that up into the sum of 2 integrals. X cubed doesn't depend on y, so happy days. Okay. Polars. Okay, it's starting to get a little bit more difficult now. Or is it? Or is it? Can I use the method that I just showed you on this problem? Absolutely I can. Absolutely I can. The only thing you would be worried about is the limits of integration. Okay? But they're all constants. So what have I got there? What's my shape? It's a rectangle, but it's a special rectangle in polar coordinates called a polar rectangle. Okay? So in polar coordinates, this is how you would talk about a rectangle. Okay? Not this. Okay? But this. Oh my God. Okay? The limits are still constants, so that's all you need to know. Okay? That's all you need to know. So, have I done it again? Yes, I have. So I've broken this up like that. Okay. You don't have to do that. You don't even have to draw a picture unless you're asked to. And let's be honest, you won't get that in Mobius, right? So, integrate this to r cubed. Integrate cosine to get sine. And simplify 16. Okay, so this is an entry level one, starter pack, polar coordinates, but you don't really need to know anything about polar coordinates to do this problem, let's be honest. Right, you're just given it and you've got to compute it. Okay? Questions? What would this look like? What would a picture of this look like? If we were asked to draw it, what would it look like? Well, theta is between pi and negative pi on 2, and r is between 2 and 0. Okay? So r between 2 and 0, that sort of gives us something like that. And then the angle is between negative pi on 2 and positive pi. So that's my 0 angle. I want to go down there, start there, and then go all the way around there. So that's my region of integration. Yeah? Now, there's also something about this question that is a little bit triggering. Notice the d theta and the dr are sort of switched around from most of the ways that you're doing the problem. Does it matter? Does it matter? Does the order matter? What happens if, I got triggered and I say, I like to write my ones dr d theta. Could I do that? Well, I could. You could also write it like this. Okay? Because the limits of integration are constants, the order of the integral can be swapped without any kind of worries about changing the answer. Okay? It's not relevant for solving the problem, but it's still interesting to know. Yeah? Okay. So, did I get it right? Let's see. How did I do? Yes. Okay, same one. All right, now we're getting into DEs. Okay, differential equations. Yeah. All right. So there's a little game. There's a little game that you play when you're given a differential equation. And it's a classification game. You want to classify or sort your differential equation into a certain type. Okay? So one thing that I learnt many, many years ago is an amazing technique to do this, right? So I'm going to show you this amazing thing. Okay, I'll go back to this in a second. All right. So shields. So when you go into battle with the differential equation, you want to bring your shields with you to protect yourself. Every letter represents a type of differential equation. Okay? So I did a YouTube video about this. It's my most popular video, right? So I think it's worth at least talking about. So the S stands for separable. Okay. What do you think the H stands for? Yeah, homogeneous or homogeneous. All right, I'll leave the I alone for a second. What about E? Anybody know? We haven't really covered E in this course, but I'll get back to that. What about L? Linear. Okay, and for linear problems, we use something called an integrating factor. Okay. What about the D? Oh, are you for the next lecture? No, you're where have you been? We've missed you.
And the next lecture as well.
Yeah, I know. I just threw someone out for coming in too early, but I know it's you. All right, the D. Sometimes you can solve a differential equation by direct integration. So let's say you had something like this, y dash equals 2. Okay? There's no magic formula for that. You just integrate it and you get y equals 2x plus constant. Okay? Sometimes you can do that. The last one, S. Anybody know what S might stand for? Substitution. Sometimes you can take a differential equation and make a substitution, just like you do with homogeneous first order problems, and you make it real simple. Okay? So the question is, what does the D stand for? And we haven't talked about this, but there are also exact, I'll put that in brackets, exact differential equations. Basically, the differential equation that you start with is exactly the derivative of something else. Okay? It's exactly the derivative of something else. Okay? So that's I've had that in my toolkit for like 30 years, right? It's brilliant. It is brilliant. So, use it wisely. Don't leave it hanging, because that is half the battle sometimes. You're given a problem. In order to solve it, it's important to classify it, okay? So separable, homogeneous, integrating factor, which is something we use, it's exactly the derivative of something else. Linear, direct integration, or substitution. Okay, let's put this to work. Let's put this to work. All right, so I've split the screens for people in the room. At home, you can't see both screens, I don't think, but just bear with me. Okay, so the first question is, find the solution to the following differential equation with some initial condition. Okay, what kind of differential equation is it? Is it separable, homogeneous, linear? Can we use a substitution? What is it? And it can be more than one. It can be more than one type, right? So what do we think? Linear. It's definitely linear. It's definitely linear. Is it homogeneous? Can I write it like this? Right, then for everyone at home. Can I write the differential equation as this? Well, let's have a look. Need the hotkeys, hey? Faster transitions. Can I write it like that? I don't think so. Maybe you can, I doubt it, right? Is it separable? Can you separate the variables by division or multiplication? I don't think so. I don't think so. Right? So, can I solve it by direct integration? No. I don't think so. Can I solve it using a substitution? Substitution is always a last resort, by the way. Right? Substitution is always a last resort because you start at the top and you work your way down, and when you get to substitution, you're out of ideas. Okay? You go to ChatGPT or something. What about exact? What about exact? Well, in this context, I guess I can say something like, let me just move this over. For everyone at home, you see this e to the x, I'm going to move that e to the x over to the other side. Okay? So just bear with me for a second. Okay. Is that exactly the derivative of some product? Yes, it is. What's the product of functions? Y times e to the x. Yeah. So this thing on the left is exactly okay? So just by moving things around, we can see the left-hand side is exactly the derivative of something interesting, something good, something helpful. I didn't need an integrating factor. Even though it's linear, I didn't need the integrating factor. The integrating factor is there. Okay? Work smarter, not harder. Okay? So it's not always that nice though. It's not always that nice. So what do you do if you don't recognize that? Okay? What do you do if you don't recognize it? Okay, so here it's linear. The integrating factor is this coefficient here. Okay, we multiply, so let's call this star. Multiply both sides by u and collapse. When you multiply over here, the e to the negative x disappears. And we actually have the same thing. So from this side, we want to integrate both sides with respect to x. Okay? And the last thing we want to do is use the initial condition to get the c. Okay? So make y the subject, move things around. And then we find c from the initial condition. Okay, so put in x equals 0 there, that's going to be 0. Put in x equals 0 there, we're going to get c equals 2. So the final answer, this is great, I feel like I just write over the top, don't have to think at all. Okay, so again, this is peak math 1, 2, 3, 1. It's peak math 1, 2, 3, 1. Questions? Let me just move that down a bit so I get the original problem back in focus. Yeah. Questions? It's not difficult, it just takes a few steps. But if you saw that you could just move things around, like this triggered me, right? The e to the negative x triggered me over there. I'm like, what is that doing over there? I'm going to move you over here. And then I don't even need an integrating factor, right? I don't even need an integrating factor. Just got to be able to, move stuff around sometimes. Okay. Other questions, comments? Everyone's really quiet at home. B theorem, yes. That deserves a thumbs up. Thank you, Kasim. I'm also noticing that the chat doesn't seem anonymous anymore online. I think that's been a change as well. If you can have a look, you can see people's names now. So maybe that's like people are not so anonymous. All right. Let's do another one. Okay, all right. So let's see if we can use our little table again, because it's something that's near and dear to me, right? When I posted a YouTube video about this, I put a really catfishy title for the video. It was like how to solve any differential equation, right? Which is impossible, right? And then I showed them this, and it's like that YouTube algorithm is so funny. You can just say anything and you'll get attention, even if it's wrong. Right? All right, let's go to the next question. Okay, all right, so I'm going to put this one up at home. So we've got my little table here. Let's go through it. So bring your shields, classify the equation. What kind of differential equation have we got here? According to the law of shields. Separable, yes. Let's try it. Can we separate through multiplication or division? Bring the y over there, bring the x, bring the 2 up there. I think we can, right? Separable is probably the easiest, I think. It's the entry level one for DEs, okay? So, yep, let's try it. Oh, is it exact? Is it exactly? Oh, here we go. We're getting deep now. Is this exactly the derivative of something else? Because I didn't see it this morning. I think I see it now, though. Let me move it around a bit. So I'm going to separate a little bit, but not sort of entirely. So let me go back to here. Okay, let me do this. Yeah. So I'm going to bring the 2y over here. Okay? So my question is the left-hand side the derivative of something? It's a product. Come on, I'm really excited now. Yeah.
Isn't it like the differentiation of
Ooh, say that on the mic.
It's the differentiation of y squared if you consider y as a function of x.
Ah, exactly. Right? This, if you differentiate y squared with respect to x, you get that. So not only is this problem separable, it's also exact in the sense that it's exactly the derivative of something nice. Okay? Now you don't have to do it this way, and in fact I probably wouldn't recommend that you do it that way. I would just separate the variables and integrate. But at least this is something that you can check, right? You can check. So what have I done? Oh yeah, I've done it that way. Okay, so I've gone through my little checklist. I found that it is separable. So I'm going to bring the 2y to one side and the dx to the other. Okay? And so now I can integrate both sides. So it's a bit like the exact method that I'm showing you, but it's a little bit different. So remember, with separable problems, you separate the variables and then you integrate. Okay? Then you integrate. So over here I'm going to get y squared. Over here I'm going to get e to the x plus c. Okay? So now you've got a choice whether you get y as a general form using square roots and then get c, or you just work with the c there. That's exactly what I did. I did the second case. Right? So using the initial condition, so you square that and you sub in x equals 0. So you're going to get c equals 3, not 4. Right? And then you can say, okay, well, this is like your implicit solution. And I think in the answer, they want an explicit solution, right? So when I've turned this around, I've only taken the positive square root. Does anybody know why that is? Why I've only taken the positive square root?
Because when x is 0, y is positive.
Correct. Is that what you were going to say? Yeah. Yeah, so basically, imagine that we had a negative sign out here and we put in x equals 0. We'd get negative 2 basically, which doesn't match with that. Okay? So exactly what you said. Okay, so basically I'm saying ignore the negative solution because it can't happen because it doesn't satisfy the initial condition. Okay. So if you're putting that into Mobius, you would do that. Now remember, what I should be doing every time is checking the syntax. Right? I've already checked that at home, but you won't have that luxury. Okay? So of course you can use the preview button as much as you like, right? And then, how did I do? Oh, the green. Questions? Okay. All right, let's do another one. Okay. Find the general solution of the following equation. Now, this question is a little bit tricky because they only want part of the solution. Okay, they only want part of the solution, which sort of triggered me when I was reading. I'm like, really? Is that what you're asking? Yeah, well, okay. So you've got a DE, it's second order, and it's linear. Now here's the important thing, and so don't miss it. Don't miss out on it. in the box below, write one of two linearly independent solutions. So they don't want the general solution. They only want one part of it. Okay? They only want one part of it. So they'll give you an example down the bottom, which is really good. Okay? So for these kind of problems, again, think back to first year. The characteristic equation is the important thing. Okay? So let me switch over to my doc. I mean, this really is pretty easy. Okay, so for everyone at home, the characteristic equation, you take the coefficients from the derivatives and you write them as a polynomial, right? So, you know, you've got 1 here, -8, -15, so characteristic equation, 1 lambda squared minus 8 lambda plus 15 equals 0. So factor it, solve it. Okay, there are two solutions. The roots are really not equal, so you want exponentials. Okay. So 3x and 5x, and you only want one part of those. Okay? So if I go back to my equation, here I've put in e to the 3x. Should we see if it works? Yeah, what happens if I put in e to the 5x? Should we try it? Okay, so you choose. It's up to you. Questions? The important thing is they don't want the whole thing. They only want one bit. Okay? Not separable, exactly. Okay. Same sort of deal with this one. Aha. Oh, yeah, this is a good one. Okay. You've got an ODE, and you're even told the general solution. How nice is that? Okay? They're saying, we've done the hard work for you. Yeah, we've done the hard work for you. So what will we conclude from this? I guess -9 and -9, it's a repeated solution to the characteristic equation. Find the values A and B corresponding to the initial conditions. So how do we do that? They want us to go from the general solution to a particular solution or a unique solution. How do we do it?
We plug in values, and there's an x on B, so that's really good.
Yep. So we take the initial data, the y of 0 equals 3, the dy dx equals -4, and we plug it into our general solution, right? X equals 0. So we have to do two things. So I'm going to take this, substitute in x equals 0 and set it equal to 3. So what will be the equation? When this x equals 0 in this, what will the equation be for A and B? A equals 3. Can't get easier than that, right? So you know A equals 3, so you'll differentiate this and then plug in 0 and set it equal to -4. So here's one I've created earlier. Okay? So there it is. There's your general solution. You go up here, you say, okay, that x equals 0, so that's going to be a, and that's going to be 0, a equals 3. And then you differentiate this with a equals 3, and you set that equal to negative 4. And you rearrange and you get your value for b. Okay? So nothing difficult there. The danger there is you make some kind of small mistake. Okay, but remember you do have how did I do once. So you probably wouldn't want to put in A and then do how did I do. You probably want to put A and B in first and then try it. Just saying. All right. Well, it's been a great morning. I'll leave the last 5 minutes for consultation. Have a great day. Enjoy it. And I'll see some of you on Friday.